All right, let's get started on the problem of the day. Let's try to get everybody settled down here. You guys are so excited for OChem, I know.
We are.
All right. So the new policy for the problem of the days is they're due up front in the front of the classroom rather than the back. With the problem of the day, I really discourage people going back, grabbing their assignment, making a little correction before they head out of the room. So this ensures that you guys hand it in, and that what you hand in is your permanent final answer. So just make sure you hand them in the front. And let's go over the key for this problem of the day. This problem of the day, we're using ethanol. Is ethanol a good base, good nucleophile, weak base, weak nucleophile? What class would we put it into? Weak base and weak nucleophile. In this case, it doesn't have a negative charge. That means it's not going to be very nucleophilic, and it's not going to be very basic. All right, we've got a weak base, weak nucleophile. Does that favor one sort of reaction type? What do you guys think? E1 and SN1. Okay, so I agree with that. The first thing we have to do with an E1 or SN1 reaction is what? Yeah, loss of our leaving group. So in this case, we can have our tosylate fall off. And when we look at our intermediate, it doesn't appear very stable at first. Whoops. Sorry. There we go. It doesn't look very stable. It looks like a secondary carbocation, but why is this secondary carbocation so special? Resonance. It's an allylic carbocation. So remember, with resonance structures, you want a double-headed arrow. You can move that double bond down. And now we've got a delocalized carbocation. This is great. So now, if we think about this, we can have ethanol attack either one of these carbocations. So let's say we have ethanol attack here or up here. It really doesn't have a strong preference either way. Come on. So let's do this one first. Oh man, my pen doesn't like this problem. There we go. And with this one, we've got another intermediate product where now our double bond is right here. What could do the last deprotonation to give us our product? Yeah, the OTS minus is floating around in solution. So I'm going to draw that as our base. A few of you guys were asking me, can ethanol do the deprotonation? Yeah, ethanol is a weak enough base where it could do the deprotonation. Really, either of these is going to be appreciably basic. So we'll have this final proton transfer, kick this off. Shoot. And we get this SN1 product, and then we get this other SN1 product. All right, so if we look at these, it's a little bit hard to tell which one's going to be the major product because it's a resonance delocalized carbocation. A few people I saw were tempted to do a hydride shift. In this case, we aren't going to do any sort of hydride shift or methyl shift. We're just looking at two resonance structures. The last one we were looking at, let's do our E1 mechanism. Come on. Here we go. So now we've got our tosylate. We said that the tosylate will fall off. give us our secondary carbocation that has resonance. And what beta protons are we going to grab? Whoops, sorry, I forgot to move this double bond. There we go. What beta protons are we going to grab? Trick question. We could really grab any set of beta protons, but we are going to favor the beta protons that will result in the more substituted alkene. So in this case, we've got some beta protons up here. We can grab them with our tosylate that fell off. Or our ethanol. It really doesn't matter which one you use. And now we get our final E1 product. So yesterday in class I said anytime you see an E1 reaction you should be suspicious because there might be an accompanying SN1 reaction. Which one of these reaction mechanisms is going to be favored? The SN1 mechanism pathway or the E1 mechanism? E1. Why E1? Heat. All right, so E1 is always favored under heat, which means that this is going to be our major product. So SN1 is going to give us some minor products, but they're going to probably be in a lower concentration than the E1 pathway. All right, so let's go back to where we were at yesterday, and then we've got an in-class activity that we're going to work on. So yesterday in class I said we can break down mechanisms based off of the nucleophile strength or the base strength. And we said if we've got a good nucleophile that's not basic, the methyl and primary carbons are going to do SN2. The tertiary carbon is only going to do SN1. And with the secondary carbon, it could do either. All right, what is maybe one technique we could use to favor SN2 on a secondary carbon instead of an SN1? What do you guys think? What was that? Solvent. So we could change it to a polar aprotic solvent, destabilize that nucleophile, favor SN2 over SN1. The other thing we have to look at oftentimes is sterics. So if you've got a big bulky group hanging off, SN2 might not be favored. Sometimes you have to actually look at it on a case-by-case basis with the secondary carbons in particular. For good bases that are non-nucleophilic, we said we don't observe anything but E2 reactivity, and we only observe it with primary, secondary, or tertiary, not methyl carbons. And then with weak nucleophiles and bases, just like with the problem of the day, we said that it's not practical in most cases on primary or secondary carbons, the exception being benzylic or allylic carbocations. We typically see it with tertiary carbocations, and we have to be aware of rearrangement reactions. And then the last one, which was a little tricky, is we said strong nucleophiles that are also strong bases have differing reactivity depending on the type of carbon. The more methyl-like we get, or the less substitution coming off, the more likely it is that we'll observe SN2 products. And then the more substitution, the more likely it is that we're going to get an E2 reaction. So let's do a warm-up problem before we go to our in-class activity. And I'm going to choose the same starting material that we chose yesterday. So I've got bromopentane. And in this case, I'm going to react this with terbutoxide. And what does the TBU-OH mean? Or what is it? What do you guys think? It's a T. Oftentimes it's an italicized small t. So we've got terbutoxide and terbutanol. What do you guys think? It's a K. So let me actually, there's a lot of ambiguity here. So let's draw these out. All right. So this is terbutoxide, and then we've got potassium with a positive charge. And then oftentimes you see it with this below it. What's the thing below the arrow? Solvent. So oftentimes you'll see the conjugate acid as the solvent. Typically when you're running these reactions, you would just take tert-butanol and throw in elemental potassium in order to form tert-butoxide. All right, what product or products would we get out of this reaction? What do you guys think? I'll give you a minute to discuss it with your neighbor, but I want you to decide whether or not your major product will be an E1, E2, SN1, or SN2 mechanism. All right, raise your hand if you think it's SN1. Good, nobody raised their hand. That means it's probably not going to be E1 either, because if the bromine fell off, we'd form a secondary carbocation. That's not really that favorable. There's no chance of it rearranging into a tertiary carbocation. What do we notice about tert-butoxide? Is that a good base, good nucleophile, or both? A good base. Why is it not a very good nucleophile? It's too bulky to be a very good nucleophile. So in this case, tert-butoxide is one of the weird examples where it's a strong base but not a very good nucleophile, just simply because it's too large to do a nucleophilic attack. So what sort of mechanism do we anticipate? E2. All right, if we look at this compound, we've got a bunch of beta protons. We've got beta protons here, and I've got two different beta protons here and here. So if we try to predict the products, we could say, all right, we could grab the blue protons on the left, and we could get this product. We could grab one of the blue protons in the middle, and we could get our trans product. Or we could get our cis product. Which one of these is going to be our major one? The left, middle, or right? Ah.
Oh, wait.
This is debatable, right? With a big, bulky base that is non-nucleophilic, does that favor Zaitsev or Hoffman? Hoffman. So if we look at this, we would say, all right, this is our Hoffman product, which is major, since we have a bulky base. And then if we look at these two, we could say that these are Zaitsev, and these are going to be minor. And then if we had to rank our minor products, which one's going to be the least abundant in solution? Cis. So we would say that this would be first, and then we'd have second, and then we'd have third. So we could even rank them in that order if we want. Does that make sense? There's a lot of problem solving involved with these, and you do want to try to draw out every potential product and then figure out which one of those products is going to be your major product. Do you have a question? All right, so what I have for you guys is an in-class activity that was in the back, and I want you guys to work with other people on this. This is almost a clone of what you could expect on an exam or a quiz. What I would do is ask you to circle which reaction mechanism is appropriate and then give the product. And then one really important thing with these reactions is anytime you show a product, make sure you show it with the correct regiochemistry or stereochemistry. So for example, are you primarily getting cis, trans? Are you getting both? Is your product R? Is it S? Make sure you draw all of the potential products out for these reactions. If you want, you can use scratch paper and actually draw the full mechanisms on these, and then I'll ask for volunteers to come up and share their answers with us.